so we're starting a new section that deals with atoms and something we call moles. This is definitely a calculator chapter, so make sure you got a pretty good working calculator for this. There's a couple of videos I want you to make sure that you watch. You should have seen it on your classroom assignment board there. Watch those two videos before you go on with mine. Okay, so if you haven't watched, just pause right here or stop right here. Go watch those two videos and then come back. Okay, now that you've seen those videos, we're going to get into something that I'm sure you're quite familiar with: protons, neutrons, electrons, and atoms. It's not always been known that atoms existed. This has only been around for a couple of centuries as far as hardcore understanding that these are a thing. So we're going to get into more in-depth concepts of what you've been taught up to this point. So we're going to build upon what you know, that of course electrons are negative, protons are positive, and neutrons are neutral. And we're going to get into how we can predict the number of protons, neutrons, electrons of a particular atom, or what we call isotope. So the gentleman on the screen that was going through the history that we were looking at, his name is Mr. Green. He had a lot of really good stuff on there. We're not going to use all of it just yet, but in time we will be using all of it. We did discuss some of these people that brought here that I want you to be familiar with, because on the quiz related to this, as well as having questions about the number of protons, neutrons, electrons, you'll also be asked to know some of the important names in chemistry history. For example, John Dalton proposed the modern atomic theory. Now, he wasn't 100% correct on everything he said. The main thing he said was that atoms are a thing, where the Greeks said wood is made of wood particles, and the air is made of air particles. They did not understand that there were particles much, much smaller than what they perceived as being a thing. J.J. Thomson's the guy who discovered the electron. He was one of those guys screwing around the lab, shot a beam of what he thought were electrons across a magnified field, and found that it being bent towards the positive side. So he found that they were negative particles for what he thought were neutral particles, and from there the electron was discovered. Ernest Rutherford, extremely important scientist, discovered the proton and the nucleus by shooting alpha particles, which are radioactive particles that are positively charged. He shot them at a very thin strip of gold foil and found that almost all of them went straight through without bouncing back, which was weird because it's a solid. It's a thin solid. It should have been rebound, but it went straight through. Every once in a while they go off at weird angles and some of them would come straight back out. And so he then proposed that since you're shooting positive particles at something and they went off in weird directions, that he found something positive, and that was the proton. He also found that the atom was basically a gigantic shell with a big BB stuck in the middle of it. And that BB was the nucleus. That virtually all the mass of an atom is in that little BB that we call the nucleus. Dmitry Mendeleev was instrumental in organizing all the all the elements in terms of number of protons. Even though he may not have known that at the time, because protons were not discovered another 20 years after he designed his periodic chart, which was based mainly on relative masses. Niels Bohr, an amazingly intelligent Danish scientist, he developed the first model of the hydrogen atom, and what you were taught in middle school as to how electrons travel around in spherical or circular paths around the nucleus was due to his ideas. They didn't necessarily hold true on everything, but the man was brilliant. He had no instrumentation to make the predictions he did, and he made much more predictions than just the model of the hydrogen atom. But he also came up with the idea of there are certain levels of paths that the electron can take. They don't just randomly take certain paths. There are specific sizes of paths and shapes of paths that the electrons travel on. That was Niels Bohr. And Albert Einstein was really the first one to prove that all these things that these guys were saying were indeed factual. And then he was able to basically tell the scientific community that, yeah, everything you're saying is true, and I have the mathematical proof for it. Part of which was this E equals mc squared equation that most people find very, at least they know what it is. They may not or know that it exists, but may not know what it is. So let's get to the atom. You should have your periodic charts available for this. If you don't have it, pause it and get it, and then continue on. Hello, who are you? Alright, so the atom is defined by the number of protons that it has. The number of neutrons, electrons can change and still be the same element, but you can't change the number of protons to have the same element. Now, that value, at least on this periodic chart, are the whole numbers in each of these charts. The hydrogen is 1, helium is 2, lithium is 3, beryllium 4, boron 5, blah, 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 blah. Those describe the number of protons in each of those elements, which you probably know already, but we have a specific name for that, and that is the atomic number. So like, if we take a look at lanthanum. So we find lanthanum on the periodic chart. Lanthanum is element number 57. Now the question here is how many protons and electrons are found in an atom of lanthanum. The thing we have to remember about atoms are neutral. If we use the word atom for a substance, we are assuming that there is no net charge. Now if there is a charge, we call those ions. And the definition of an ion is a charged atom, which we'll deal with a few chapters down the road. The lanthanum, though, because it's element number 57, is going to have 57 protons. So that means 57 positive charges crammed into the nucleus. So if it's neutral, then you have to have 57 negative particles traveling around that. So the electrons and neutrons protons must be the same. And so there are 57 protons and 57 electrons. Okay? Again, periodic table has all kinds of information, and that's a big one. Now, the neutron, what the heck is going on with neutrons? Why do we even bother? I mean, well, we don't put neutrons in, but why does nature put neutrons in there? Well, as Mr. Green was saying, that you have all these positive particles packed in a small area. They're all the same charge. They don't like being the same charge close to each other. So if you're going to cram them in there, you got to have something to buffer the repulsion that's going to take place, and that's the job of the neutrons. The neutrons basically keep those positive charges from repelling from each other by allowing basically an area where the repulsion is kept at bay. Okay, so the number of neutrons is going to vary depending upon what we call an isotope. An isotope is the same atom with a different number of neutrons. Okay, so it's the same number of protons, same number of electrons, different number of neutrons. Now, the neutron and the proton are very close to the same mass. So close that we basically say they're the same. They're not the same, but they're so infinitesimally different that we say that, oh yeah, that's pretty much the same. Electrons, however, is about 1/2000th of the mass of a proton or neutron. So it's virtually nothing. Now you got this, like I said, like a very dense BB packed with all these protons and neutrons, with basically the entire mass of the electron, or of the atom. Around the atom, you have these electrons buzzing around in different shapes and sizes and all that, depending upon something we'll get into called electron configuration. But the mass of the atom is based upon the number of protons and neutrons. So if we add the protons and neutrons together, that is called the atomic mass. Okay? So, if we take a look at lanthanum 139, so we're back with lanthanum, element number is 57. We have two ways of representing those isotopes. We can write it in this form right here, where we have the name of the element, and then a hyphen, and then the atomic mass. And then again, this is total number of protons and neutrons. Over here is another way that we describe it, and that is by writing the symbol of the element and putting the number 139 in the upper left-hand corner of it. Now you'll see also some isotopes written with the element 57 down here. I don't put it there mainly because you can look that up right here. Just know that this is the starting point for the number of protons and neutrons. You look at 57 for the number of protons, and you subtract 2 to get the number of neutrons, which is 82. Example. Find the number of protons, neutrons, electrons for nickel 58. So we find nickel on the periodic chart. Nickel is element number 28, right there in the middle of the chart. So you could put a 28 down there to help emphasize that. If you want to do that, that's not a bad idea. There's nothing wrong with it. So, if that's 28, then you know that there are 28 protons, and there are 28 protons, there's 28 electrons, and then we subtract 58 minus 28 to get the number of neutrons. That'll be 30. So we have 28 protons, 20 electrons, 30 neutrons. Example. You have two ways of writing the isotope of rhenium, which has 111 neutrons. Okay? Now, the isotopes that we've written here, in the previous point right there, is written with the atomic mass, not the number of neutrons. So we have to find rhenium on the periodic table, and rhenium is element number 75. It's right here next to tungsten and osmium. So that's element number 75, and that means the total mass is the 75 protons plus the 111 neutrons, which would be 186. Alright, so we add those two up and we get an atomic mass of 186. Now, we don't necessarily put a label on there, but if we were to do that, we will call it the atomic mass unit, and we will get into that later on. But an atomic mass unit is exactly what the name describes. All the masses of atoms are determined by the number of protons and the number of neutrons. We call those each particle a unit. So we have 186 particles in the nucleus that gives it the mass. So we call them 186 atomic mass units, or 186 AMUs. Don't have to worry about that just yet. Just know that the number here is 186. And so when we write the two forms of the isotopes, we write in this form here, 186Re, or this form right here, rhenium hyphen 186. Your practice problems then will involve finding protons, neutrons, electrons, and finding the isotopes like we did in the last example. So there's I problems. Okay? Good luck.